We'll go live. All right, welcome back. We are GAME3001 in the summer 2021 semester, and it's week 5, part 2 of our broadcast, and we're talking about, well, lab 5, we're going to be calculating the tile costs for each of the tiles. We're also going to make references for the top, right, bottom, and left. So this is all part of lab 5. We're going to calculate or compute the Euclidean distance to the target, as well as the Manhattan distance to the target in prep for next week, as well as toggle between Manhattan and Euclidean distances, and prep for pathfinding by setting up the data structures and all this other stuff. So we're going to kind of do some prep today. Today's more of a prep lab as we build everything we need, all the structures we need for pathfinding for next week. So that's what we're going to be doing today. To start, what I've asked is that you guys can start with a starter code. Lab 5 starter is what we're starting with. And I'm going to go there. That's just really Lab 4B from last week. We're going to start from there. So I'm just going to pull that up. So there is Lab 4B. I'm going to right click and 7-zip extract to there. There is Lab 5B, which is your lab. Okay. Lab 5B, I can get rid of this now. And in here, let's launch Lab 5B. And one day when Visual Studio decides to launch, there we go, it'll launch. Okay, good. So for this, just like normal, what we want to do here is we want to shift from x64 to x86 like normal. And we want to retarget your solution. Let's retarget solution so that it is your SDK, not mine. So now it's runnable. Let's change the, in the documentation, let's go in here and change the README file so that it doesn't read lab 4, but rather says lab 5. And let's also change inside of the scenes in the playscene.cpp where we have the name that comes up with IMGUI up here, right, which is here. It should say lab 5. Save that. So this is ready to go. And I think if I was to run this thing, we should check to see if it runs and works. And if it works, we can put this up on GitHub. And that'll be our, yeah, I know, Lyra, it takes a bit of time for ReSharper to come up with everything. Well, let's see how this works. All right, so yeah, we have Lab 5B, we have this stuff, and when we turn the grid on, we have what we had last week, which is this, okay? This is good. Let's put this up on GitHub. So again, I'm gonna go to my Solution Explorer, and I'm going to right click. I'm going to go to create Git repository here. And just like I did last time, I'm going to select George Brown College and change the template to GAME3001 in the summer 2021 semester. And it's Lab 5B. And that should kind of set us up. I'm not going to make it private. It's going to be public. So I'm going to uncheck that one and then press create and push. So that should do everything we need to get that repository going, all within Visual Studio. All right, and then let's go up and check it up online. So if I go to George Brown College and I see Lab 5B there it is. I want to grab this link, and this is going to be our final. So in here in Lab 5, I'm going to make a new web link, and this will be the Lab 5 final, okay? So that way you have the starter and you have the final. You can see the difference between the two and then work your way through from one to the other, okay? And that's where we're starting. So we're starting here, all right? We're starting here. And what I want to do is I want to start thinking about calculating the tile costs from one tile to the other. And there's a few different use cases here that we're going to cover today. One of them is, well, what if I want to find my neighbor? I want to find the top neighbor. Let's say I'm here, the right neighbor, the bottom neighbor, and the left neighbor. Right, so I want to find all these neighbors here, top, right, bottom, left. I'm going to go into this right winding method. I'm going to use that way of doing it. And if I'm in this tile right here, let's just use this kind of a square here. So if I'm in this tile, then this is the top tile, this is the right tile, the right neighbor, the bottom neighbor, the left neighbor. And this is the case when I'm in the middle. So this is one case, case one, right? There's also a case when I'm on the top left. If I'm on the top left, then I don't have a top tile or a left tile. These should be null pointer, but I do have a right tile and a bottom tile. So that is case number 2. Case number 3 would be if I'm here, 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 or here, right? And what those are, there's more cases actually if you were to figure this out. So I'm in the top tile, but I'm not in a corner. I'm not in the left corner. Well, I have 3 tiles. I have the left tile, right? I have let's say I'm here. I have the bottom tile, and I have the right tile, but I have no top tile, right? And the same thing goes for these ones. So I can do this one where I have the top tile, the left tile, and the bottom tile, but no right tile, right? So it's another case down here somewhere where you get it, right? Where I have the top and the right and the left, but no bottom. And then over here, where I have the top, the right, and the bottom, but no left, I have this tile here, which gives me the top and the right, and this tile here, which gives me the top and the left, and this tile here, which gives me the left and the bottom. So those are all the different cases for all the different tile types. Somewhere in the middle, with that has 4 neighbors. The corners, which only have 2 neighbors, right, and the sides, which only have that have 3 neighbors. Okay. Does that make sense? So I want to be able to make associations, and remember, neighbor tiles are connections, and my tile is the node. So it's like I have 2 connections from this tile. I have 3 connections from this tile. If you can picture this as connections, right? And if I was to annotate this a little bit, it's like I'm doing this. I'm making a connection here and a connection there. And these ones, because on the right, I have a connection here and I have a connection there. Those are my connections, right? So I'm making these connections, right, for each of these tiles, right, as I'm working down. I don't have a connection that's to the left because, that's all the tiles. That's what the connections are. The connections this way. And these ones have 3 connections, right? I have 3 connections to those tiles, and this one has 4 connections. So these ones in here are denser, the ones in the middle, right? Because they have 4 connections for every node, right? And this is where we talked about it before, where the tiles, the tiles that are in the, when I use tile and grid system, we've got to take care of something like 1,100 connections. Plus 300 tiles for just a tile system that is 20 by 15, right? So this is where it's a little bit heavy in terms of memory management, right? We have that many pointers to worry about, as an example, plus this, additional memory allocation for each of the objects. So we have 300 memory locations for tiles, plus 1,100 pointers that we're going to keep track of, okay, or thereabouts, 1,104, or something like that. Okay, so let's do it. So that's what we want to do, and we'll keep this up here for now, and then I'll erase those. Let's go back to this and do that thing. So inside of, so the first thing we want to do is when we start thinking about building our grid, we did it in the placing, right? So in the placing, we have this build grid method, which is right here, right? This is our build grid. And in our build grid, all we did for build grid was we just made the tiles and we printed them out, adding labels, and we set the labels enabled or not. We pushed the tiles onto the grid. Well, what we want to do is similar to this with build grid, but what we want to do is make those tile associations, right? The tile associations, right? So I want to still do this double loop, right? And I definitely want to do it after the grid is built. I can't make an association with tiles in the grid until there is a grid, right? So let's grab all this. And what I want is I'm going to make associations or create references, we'll call them connections, right, for each tile to its neighbors, right? So neighbor nodes, right? So from each references from connections from each tile to its neighbor nodes. Each tile from each node to each of its neighbor nodes. That's what we're doing. I'm putting node and nodes and connections so that you know that's what we're doing. We're making a graph, but we're using a tile and grid system to do it. We don't need all of this. That stuff was just there to set up our grid in the first place. And we're using a double for loop because, well, it makes sense, which is what you're going to see in a second. So the first thing we want to do is I want to use a temporary tile, just like we've done up there, right? So I'm going to say tile. Well, instead of making a new tile, we don't want to make new memory. We want to point to the tile that I'm looking at in the grid, the current tile that I'm in the grid. So I'm going to say m_get_tile, and I'm going to look at tile column row. What that means is that in the first run, I'm looking at 0, 0, tile 0 column, and then 0 row, which means if I go back to Excel, I'm looking at this tile right here. Okay? Now, I want to check a bunch of different things. Are we in the topmost row? Right? Are we in the rightmost column? Right? Are we in the bottommost row? Are we in the leftmost column? Because those are specific conditions that are going to affect us, right? So those are the almost going to take care of some of our cases, right? If we are in the topmost row, how do we check it? We're going to say, well, if my row is equal to 0, I'm in the topmost row. If I'm in the topmost row, I want to set my neighbor tile, which is the top tile. I want to set that top tile to null pointer. Null pointer. Right? Does that make sense? Because we're not pointing to anything else. It's going to be something null. And when we do our neighbor check, if the tile we're looking at is a null pointer, we're going to ignore it. We're not going to check tiles when we do our pathfinding that's a null pointer. Right? Similarly, right, let's build this out a little differently today, this time around. If we're in the rightmost column, that means our column is in the right area. So config column number -1, because whatever the column number is for 20 minus 1 is 19. If I'm in the right column, then my right tile, right, that's going to be null pointer. And what about if I'm in the bottommost row? So let's grab the row thing again, right? Because row. If I'm in the bottommost row, then the row then is equal to config.row number, right, -1. If I'm there, right, if I'm in the bottommost row, then the bottom tile, this one, is null pointer, right? And finally, if I'm in the leftmost column, which is just like the rightmost column, grab that, then instead of column number, well, then the column is going to be 0, right? If the column is 0, I'm in the leftmost row, right? And so therefore the left tile is null pointer. So this sets up all of our null pointers, all the conditions we just talked about. And no tile can be all of these things, right? Some tiles might apply to more than one of these conditions might apply, or these conditions might apply to the tile. For example, more than one of these things. Like, for example, I can be top right or bottom left, as an example, but I can't be top and bottom. Those two things are exclusive. I can't be both of those, right? But I can't be these two, or I can be these two, or I can be these two, or these two, right? So the only thing that doesn't make sense, and I can't be these two. I can't be right and left, right? So those kind of are exclusive. And there's ways of improving this check. But here's what I want to do too. What about if I'm not this? I'm not in the top row. then I want to start thinking about my, top neighbor. I want to set up my top neighbor. Set top neighbor up, right? If I'm not in the rightmost column, right, then I want to set up the right neighbor, right? If I'm not in the bottom column, then I want to set up the bottom neighbor. When I say my bottom neighbor, my connections to my bottom neighbor's node, right? The bottom node. And finally, as you can guess, if set up the left neighbor, right? If I'm not in the leftmost column, right? So how does that look? Well, if I want to set up my right neighbor, then I'm just going to go my top neighbor. I want to say my top neighbor then, my top tile is not null pointer anymore. Instead, let's get the m_get tile. Let's get the tile that's inside of the current column, but my one row above. So we're my column and then row -1, right? Oh, what do I mean by that? Remember, get tile gets a tile pointer. That's what it does. That's what get tile did for us. Column is the current column, and then row -1 points 1 up. So that means that going back here, if I was here, then row, same column, but 1 row up is here, right? So that makes sense. So that's this one. Similarly, if I'm going to look at the right tile, let's do the same thing. So I'll grab this and I'll put that in there. And I'll say that, well, if I'm looking at the right tile, let's see if we can figure this out. m_get tile. I'm looking at the same row, but then my tile is my column is +1. So column +1 and then the row. Does that make sense? So that way we're only pointing at the stuff to the right or left or whatever. That's the right neighbor. Okay, this is the bottom neighbor. Okay, so let's grab this. And we'll say for the bottom tile, we'll use that utility function, m_get tile again. And we'll say that it's in the same column, but it's row +1, right? And then finally, for the left tile, we're in the same row, but it's column -1. Okay? And of course, I should probably put it in the function. Okay? It would be nice, thinking of what I just did, right? It'd be really cool if, as an option, I had an overload that I could kind of look at the integers here instead. Maybe my set neighbor tile as an overload could take numbers like 1 and stuff, so I don't have to do mget tile at all, as an example, right? That might be really cool as well, right? Yeah, close that door. All right. Whew. Noise, noise, noise. All right. So does that make sense? Hopefully that makes sense to all of you. Let's get into the next piece, which is, okay, fine, I've looped through all this and I've already created my grid. Well, let's, I don't know, do some troubleshooting and print it out. And so one of the things we do always is we look and see if we can do some debugging and see how this looks. So I'm going to do some debugging here. So we're going to do a standard cout, and we'll say something like grid size. Let's print out the grid size, or we can say m_p grid size, right? Okay, and what I can do is on this line, I can set up a breakpoint. So when I run this thing, we can check to see if this all works or if it's going to blow up. Okay, so it stops us, right? And it automatically says that the says see out it's undefined, is what it says. But what it does say is that grid size, this is interesting, it says that grid size is 300, okay? And this is good. It tells us how much memory is being allocated. We're sitting here at the breakpoint. What I can do is I can start inspecting the grid. So if I look inside the grid, I can see that there's a bunch of tiles here. This is tile 0, right, inside the grid. And then I can look at the tile cost is 0. The status is unvisited, right? The cost label, right, is what it is. Look, it says 99 with a console is 12. And the status label is dash dash. That's what it is there, right? Neighbors, I have 0 in the 0th neighbor. I have something in the right neighbor, and there's something in the bottom neighbor, and then there's 0 on the left neighbor. Well, of course, this makes sense because guess what? I'm in the top left corner. So the top, right, bottom, left, top is nothing, null pointer, and left, top left has nothing, right? And this is working great. You can check because each tile, doesn't matter which one I check. Let's say, for example, I want to check one that's kind of to the right. So the 15th one, or let's say the 19th one, here's the 19th tile. Let's look at this one. The 19th tile, if I look at the neighbors, now is going to be the opposite. Top and right are both null, but bottom and left are okay, right? That's that case. So you can see that this is totally working, okay? And we can do that for a lot of stuff. We can inspect anything that's in here that hasn't terminated. For example, I can't inspect the tile because this tile is out of scope, right? It kind of started here inside the for loop and then it died within the for loop itself. So when I come back to this point here, my breakpoint, it doesn't really show anything. Let's stop that and let's delete the breakpoint by right-clicking and delete breakpoint. And I don't need the grid size. I printed this out as a contrivance just so that way I can have a place to break inside this function. Okay, there's other ways to do that as well, but this is kind of an easy way to do it if you wanted to show it. So we know it works. This is great. Let's put this up on GitHub. Before I even run this thing, I mean, if I run this thing now and it runs, that's what I got to do. So it runs, and I can do this, and I can show the grid. But this is good. We don't error out, and we know we made our references. We have all the references from one tile to the other. Let's put this up on GitHub now. So again, I'm going to go to here. I'm going to say added references to each tile's neighbor. Okay, commit all and push. Okay, part 1 is done. So we've done this part. Okay, and I like trying to check these off because this is kind of what we want to do, right? Slowly, slowly. I want to knock off each of these things, each of our goals for today, right? This is our kind of our Lab 5 goal. One thing I want to start thinking about is what is it going to look like when we create our computation function, right? So let's start computing the tile cost now. So again, going back to this, in the placing.h file, I want to start thinking about putting other functions in here. And one of them is going to be the compute tile cost function, right? So we have our set grid and build grid and all this kind of stuff. And I want to start thinking about, building out our functions. We're going to say void, right? m_compute tile costs. That's what I'll call it, right? And let's set up this function. Generate the implementation here. There's my compute tile costs. How is that going to work? Well, let's think about doing it for Euclidean distance first, because that's what I said I wanted to do. Let's do it for Euclidean distance first for each tile, for every target, from between the tile and the target and each tile. Okay, and then it's updated in IMGUI afterwards. Okay, let's do this. So how do we do that? So when we start computing the cost, let's do an auto distance, right? And we're going to say that the distance function for this is by the way is compute the Euclidean distance. let's do Euclidean first, because that's what we said we're going to do. We'll use the util distance function for that, right? We can do that, and we're going to calculate distance. Now, we want the distance in grid space, not in world space. In world space, the distance function itself, if we go to definition for the distance function, notice what it does. It takes two vectors, vector A and vector B, and then it uses a square root function, uses Pythagorean theorem to figure out the total distance. Now, this is a expensive computation if we were going to do it every frame, but we're only going to do it once, right? So this isn't bad to do one time, right? So again, between A and B is what the distance is going to be. So what we want is, let's go back. What we want is the distance to calculate. If we want to calculate in world space, it'd be something like this: the the tile that we want to calculate in. So we want to do some kind of for loop. Let's do a for each loop, let's say. And the for each loop, remember how it works? It's kind of a arranged for loop that goes from the tile to m_p grid. That's the collection. We can just call it element. Instead of element, we'll call this tile. We've done this before. In fact, it's right here, right? And we'll take this calculation, and now we have a tile for each tile in the grid, is what we're saying. Go to the tile, and then we can get transform position. That's going to give us in world space. That's not what we want. From the tile to m_p target, and then get transform dot position. That'll give us the distance in pixels. Distance in pixels for our situation right now for computing the tile costs means nothing. Doesn't mean anything for distance in pixels. We want distance in grid tiles. That's what we want. So instead of this, we can change this to get grid position. And the same thing goes here, because both the tile as well as the target are navigation objects. That's what they are. Remember, we kind of made a new class last week for navigation, right? So we can calculate the distance between, in terms of, in the grid. So compute Euclidean grid distance, right? Between tiles for each tile and the target, whatever the target is. Okay, that's what it's going to do. And then what we want to do is we want to, once we've calculated this distance, right, we want to set the tile cost for each of the tiles. I'm going to say, hey, tile, let's set the tile cost, right, to the distance. And we could certainly do this in one line, right? We can totally do this in one line. But we're separating it because it's just easier for us to look at right now. And remember what set tile cost does. If I go to definition for set tile costs, not only do we convert the floating point tile costs into a string, but we update the text label for each tile that we're modifying. Okay, so this is going to have an immediate effect. So let's try this out. So run. Well, how about doing it for the first time? We really never calculated we never computed the tile yet. Where would we do this? Let's go back one. Where would we do compute tile costs? Let's clean this up too. Well, we would do it probably, after we set up the grid. So after we set up the grid, that's inside of the start. We've set the grid up. We also need to know about the target. So let's do it after everything and before we actually print out IM-GUI stuff. So down here, we'll say that compute tile costs is what we're going to do for the first time. And this is going to actually change the labels in the grid. Let's run this thing and see what happens. So, and ta-da, this is Euclidean distance. But when we move this around, nothing happens. This is where the original position was of the target. I want to be able to recalculate every time the target moves. So in order for us to do that, then in the GUI function, after we move the target, like probably something like here, so this is the target, the goal, if you will, we want to compute tile costs again, right? So we want to do that every single time, recompute tile costs and redraw the text or whatever every single time we move our target around. Let's try that again. And if we do it now, you can see that the tile costs move around, right? This is Euclidean distance. And you can see that the distance that we're talking about, if I move this around, it doesn't do anything. But you can see the distance from this tile to here is 15.6 as the crow flies, right? And from this tile to here is 15.0 as the crow flies. What I mean by that is it's a direct line, right? It's a direct line from here, the middle of this tile, all the way to the middle of this tile. And how is this calculated? It's using Pythagorean theorem. So it's going to draw a triangle from here to here and from here to here. That's what it's going to do. And it's going to take the difference in length. So this is 1, 2, 3, all the way to 12. So 12 by 1, 2, 3, 4, 5, 6, 7, 8, 9, 12 and 9. Let's do that calculation manually for ourselves. And let's see what happens when we do it, right? So let's bring it up. So there's my calculator. So if I say 12 times 12 is equal to 144, and 9 times 9 is 81. It's 81, so it's 225. If we take the square root of 225, we get 15. And that's what number you're seeing here. All right, so that's what we're doing. We're doing this Pythagorean calculation between this tile and this tile. And that's great if we were doing something else and we didn't use a grid. But we talked about this as okay, but it's better to use Manhattan distance. Well, first of all, let's update GitHub. So again, I'm going to go to, let's clear that up. All right, and let's put this up on GitHub because this is totally working now. So what I want to do is go here, and I'm going to say computed Euclidean distance for each tile. Yeah, so we did commit all and push. That makes sense. If yours still says 99, that means you haven't, Lyra, you haven't done this compute tile costs once. You need to do compute tile costs, you know, as an example, after you have your target and your grid. You can't do the distance between the target and the grid if you do it right under here. It has to be way after the grid and everything has been updated. Okay. Okay, this is number 1. 2, now that we've got this piece, what we really want to do next is we want to make it so that we can compute Manhattan distance. So this part is done. We've done the calculation to do it this way. Well, what about if I wanted to, you know, try it out for Manhattan distance? How do I do that? So for Manhattan distance, again, I'm going to scroll down to where we have our new distance calculator, which is this compute tile cost thing. And let's comment out this stuff. So what is Manhattan distance? Let's think about that as well. And I'm going to clear this up because we've already done these things, right? So we don't need to think about any of these things at all. So let's just no border on all this stuff. So this is it. So if I have an object that is at 3, 1, and I have another object that's at, let's run the code actually and see where that leads us. Okay, so 1, 3, and 15, 11. 1, 3, and 15, 11. Let's do that. So 1, 3, right? Here's 1, 3, and 15, 11. So 15 and then 11 across. There it is, 15, 11. This is the goal tile, right? So this is the start and this is the goal. Right? Then how do we calculate Manhattan distance from here to there? We add up the number of tiles, right? So we sit there and start counting, right, tiles. And let's count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. All right, so we have 14 across this way, and then 15, 16, 17, 18, 19, 20, 21, 22. So this right here is 22 tiles away from this. So this would be 21 tiles. This would be 20, and so on. Let's try this out so we can actually use Excel to our advantage here. So up to there, 8, and this will be 7. And then we can kind of calculate the entire grid of what it's going to look like this. So this from here to here is 21 tiles. This is kind of like Manhattan distance. We count the number of columns, and then we add the number of rows away from the goal. So we do, right? And the great thing about this is if we went down one, right? And that if we were to go here, this would be 19. Notice there's a symmetry in the way this works, right? So here's a group of 19s, and then down here would be a group of 18s, as an example, and all that kind of stuff. So there's equal numbers around, and I can use Excel to help me build this again. So I can kind of do one of these, right? And you can see that this should all kind of connect, right? So I can make all the calculations I need at least two numbers to do that, based on the current location. On the other side, if I was going to go over here, this would start building up again. So this would be 9, 10, 11, like this, right? So this would be, 8, 9, 10. This would be 7, 8, 9. And this would be 6, 7, 8, like that. And you can see that there's a symmetry that looks like a diamond shape that appears. All right. And then once you have this symmetry here that's happening, you can start calculating the cost. Now, if this is my start tile, then obviously I'm going to look at all the tiles around it. So this would be 23, right? This is 22. This is 23. This is 22. And this is 23, right? Or 22, yeah. So it makes sense. So you can see that this would be 20, then, 20, then this would be 21, this would be 20, and this would be 19, just like the grid that I'm talking about. You see the symmetry that happens, that appears as I'm using, the Manhattan distance from one thing to the other thing, okay? So that is what I want to figure out. And the way we'd figure it is we add up the number of the difference between the columns from my start tile and my goal tile. So if I'm in column 1 and I'm in column 15, then the distance is 14, right? And then if I'm in row 3 and this one is in row 11, then the difference is 8. 8 and 14 is 22. And that's how we would figure it out. Okay, so that is the way we figure out Manhattan distance. Going back to this then, let's just comment the distance out for a second. And we'll just copy this, copy the distance, right? And this part. And what we'll do is we'll compute the Manhattan distance up here, okay? And we'll say auto distance. Instead of util distance, we'll keep the set tile cost once. So we're not going to change this one. We're going to do this one time, right? But the distance here won't be a distance calculation anymore. It's almost like as if I need, some other values. I can't do it all at once. And in fact, maybe what I want to do is separate the distance into its own, kind of floating point number up here. So I'll say distance is up here. We'll also use something called delta x, which is kind of the change in x values, columns, and then delta y, which is the change in y values, rows, right? And you can also say delta column, delta row if you really want to. That's totally fine to do too. We don't need to set up the distance anymore because we already have that. Just to remember that, I'll just kind of comment that out right there, right? And what we want to do is start thinking about how to calculate the dx and dy values. So dx then would be kind of like the absolute value between the tile and then its get grid position dot x, and then I want to subtract the target, right? Get grid position dot x. So I want to subtract the x's, and I want to get the absolute value, so the total number of tiles between the positions. That's what I'm saying. It doesn't matter which direction I'm looking at, right? And I'm going to save it in the dx value, okay? And then I'm going to do the same thing for dy. So dy then would be equal to, let's just copy and paste this part. Dy then would be the same thing. So where I say that I want to find the distance, the Manhattan distance between those two values. That's the y values, so the y values. And then for the distance, it wouldn't be a distance calculation. It would just be, let's add up the dx plus the dy value. So that's what the distance calculation would be here, okay, if that makes any sense. And once I've calculated the distance, I want to set the tile cost to the distance, which will be the distance in grid spaces, right? So compute Manhattan grid distance for each tile in the target. And then Euclidean is down here. We just commented Euclidean out. Let's see what happens when we do that instead. So again, run it. Let's run this thing. And we should have about 22 for the distance, right? So again, if I show it, you're going to see 22, right? Make sense? So now this is in total tiles. I can count the tiles, 21, 19, 18, 17, and then I just count tiles, and I'm down here, right? And this works best for a grid and tile system, like we mentioned last week, because we're kind of in this squarish situation, right? Rectangular situation, we're going to use Manhattan distance. That's kind of the more accurate way to do it. One thing we're going to be disadvantaged in is that we can't move diagonally. So we can't go from here to here to here to here, because in the assignment that I've asked you to move, we're not calculating diagonal neighbors. We haven't used that. So we're going to have, at times, some kind of tiebreaker we need to do between two values. So the 21 on the right and the 21 down, that's the same thing, but we're winding in the right order, which means we're going to take the first value that's the lowest value. So in other words, if I'm winding in the right order, I'm going to say, if I compare these values here and I want to move to the right over here or down, I'm going to move right first. Okay, I'm going to take the rightmost value first. So if I'm here and I want to find the next value, 20 and 20, I'm going to move to the right. So this is actually going to march all the way this way and then all the way down. That's what's going to happen. Okay, when I use Manhattan distance. For Euclidean distance, it's not going to do, it wouldn't do that. It would do this. It would kind of step down this way. Okay. At the end, it would be the same. All right. So that is, Manhattan distance, and we've done that. So let's put this up on GitHub. So we'll say, kind of computed Manhattan distance for each tile. Okay. So we did both. And we're kind of here. We did both these two things, okay? What we want now is we don't want one or the other. We want to be able to use some kind of toggle between Manhattan distance and Euclidean distance in IMGUI. For this, we need another construct, all right? And what we can do is, if I go to Solution, the Solution Explorer here, I have already an enumeration that I've included with your structure. We just need to include it. It's just grayed out right now. It's not included. We're going to include an already existing structure. So again, in enums, try this. I'm going to right-click and add an existing item. And you're going to choose inside of the SRC folder, there is a file called Heuristic. Okay, it's been there for the whole time. If I click add, it's going to give me a new enumeration, which is going to look like this, where I can switch between Manhattan and Euclidean, and it's just a number. 0 is Manhattan, and 1 is Euclidean. It doesn't matter if you put them the other way around. Okay, so that's Manhattan and Euclidean. Cool. Now that we have the heuristic enumeration, then what I want to do is I want to, in the placing.h, down in the bottom here, what I want to do is I want to, keep track of the current heuristic. So heuristic. We can say that heuristic, right? We can include heuristic.h now. We can say that m_current heuristic, right, is what we want to call it, current heuristic. Whatever the current heuristic is, we can switch between one and the other. And where we want to set this up is in the placing.cpp in the start method. So in the start method, right up here underneath the offset, let's set the current heuristic. So say m_current heuristic, and we'll set that to Euclidean. Okay. Again, you can set this up any way you want. I'm just setting up as Euclidean first. We're kind of initializing it to something. It says prefer enum class. We're not using enum classes right now. All right, so that is the first step. Now what I want to do is in my computational function, which is the compute tile costs, I want to reform this a little bit to make it so that it makes more sense. So I'm going to use a switch case for each tile. So I'm going to say switch. And what I want is, depending on the current heuristic, right, I want to create two possible cases. Case 1, which is Manhattan, do something, and case it's Euclidean, do something else. Okay? Make sense? So for Manhattan, we want to do this piece. So let's cut this out and put it in there. And for Euclidean, let's comment this in, right? And we want to take this piece, cut it out, and put it in here. Either way, we want to calculate the distance based on, as an example, it says might not be initialized here. If you really want to initialize the distance, then what you can do is you can set up separate things here. We can set up the distance as 0.0f. They need initializers a lot of times, right? At least for C++ not to complain. I can also make this all in one line and blah, blah, I just don't like that, right? It's just a matter of coding style. You might like to put it all in one line. It might save you a line of code. Who cares? Okay, this is just for clarity. So there we go. So we have distance and dx and dy values are pre-calculated and whatever. You can see that there, I don't have to do this. It says dx is reassigned and all paths being read. So, I mean, who cares if we do this is what it's saying. But it's okay. So this is the heuristic. And one thing it says, it doesn't have the whole range of the heuristic enumeration, because the heuristic enumeration also includes number of heuristics, because I can have more than one, right? Maybe in the future, I'm going to have other heuristics like the null heuristic or the best first search heuristic or whatever, breadth first search. And it doesn't really matter, right? I can have as many of them as I want, and then I can include all of them. That's why this is complaining. But we're not going to include all of them. All we care about is these two for now. All right, well, let's run this the way it is and see what happens. So remember, it's based on the current heuristic, which right now is Euclidean. So if I run this, and then if I move this around, you can see that the whole thing moves around. This is Euclidean. We need a switch case, some kind of switch or adjustment or toggle up here in IMGUI to switch the grid from Euclidean to Manhattan. Okay, we can do that in the IMGUI function, right? This function right here. And the way to do that, right, is start thinking about some kind of radio button or whatever. Right now, what we have is we have this grid turn on. We have a separator. Let's add another separator. So we're going to copy paste this. And what we want is a some kind of radio button in here. So we're going to say something like static int radio, right? And that is going to be, we're going to static cast, right? Because that's what it wants us to do. Static cast the current heuristic. Whatever the current heuristic is, we want to static cast and save it in radio, right? So that's the radio button we're going to modify as normal. Then we need a label of some kind. So we're going to say, hey, IMGUI, I want a text object that's just going to show the, allow us to modify the heuristic type, right? So we'll say heuristic type is, and then you can select the heuristic type by using a radio button. So radio buttons kind of look like this. Here's a radio button. We can have a label for it. For example, Manhattan, right? And then it says the next one is radio, right? So Manhattan, radio, and that's the one that we want to use, radio. And then followed by what thing that we're gonna show, if it's the vertical button or not, and we can cast it as an example. We can say static cast, right? Static cast, and we can kind of put in, it's an integer type, which is, we're just going to kind of circle it with Manhattan. Because again, we're converting an enumeration to an int, okay? Is there another overload, right, where we want to show something? We have these three things. Well, we have a couple of options, right? So label and active, that's the Boolean. That is kind of true or false. And then whatever the radio button is, that is Boolean, a Boolean active, right? So it's active or not, right? And then whereas the other option is I'm actually giving it a value. So this is a different option for me. So radio button, it says I have my integer value and my integer value button. Okay, what's the integer value button? So Manhattan. So here's my value, right, radio, and then depending on what the radio is, I'm assigning it a value, right? There's different ways to do this, but then what we want to do is we want to use same line. So I'm GUI, same line, right? And then we're going to do the same thing, but what we're going to do instead is, I don't need to have the same line. What we're going to do instead is we want to change it from Manhattan to Euclidean. And we're going to change this from Manhattan to Euclidean. So that changes the value. That kind of says that the value is whatever we decide to put it, 0 or 1 or whatever we want, right? And then the next part is we want to make a switch. So if the value is changed, whatever the value is going to be equal to the radio button, right? That's what we want. We set that the heuristic is the radio button, but only when the value is changed does the heuristic want to change back to the radio button. It's almost like I want to do, and I only want to compute costs. I only want to compute costs once. Whenever we change the heuristic, then we want to compute costs again, right? Because otherwise, if I don't do this, if I don't do an if statement here, then I'm always computing costs, and I don't want to do that. So I want to say if the current heuristic is not equal to somehow the static cast heuristic radio, right? If it's not equal, if they're not the same, then what I want to say is that the current heuristic is equal to static cast radio. Whatever the radio button is, the value of the radio button that we assign it, that's the value that I want to assign the current heuristic, right? And then what I also want to do is I want to recompute the tile costs as soon as I do that, because I'm changing the way tiles are being computed when I switch this on and off. All right? So that should give you an idea of what to do. Let's try this out and see if it works. So trying it out. And we turn the grid on. And now this is funny. This is a glitch. It doesn't really show me which one is on. Okay. So turn it on. You can see Manhattan, right? Turn it on. You can see it's Euclidean. You can't even see the tiles in here or the thing. I could use a toggle where I turn, you know, I know it's just a glitch in our little thing. I could use a toggle instead, and a toggle would be like Manhattan or toggle Euclidean instead of Manhattan. You could do just like a bunch of check boxes. So if I check on Manhattan, it's checked on. If I check on Euclidean, it's checked on. And I can't toggle one or the other, but whatever. I'll leave it like this for now. So it works, but it's like I want to turn on the object. Let's suppose I had another option, and let's just do this as an example. So I am GUI same line. This is where it freaks me out, right? There's some kind of glitch. I'm not sure what it is. It's my fault, not your fault. And let's suppose I use some kind of other radio button, and I'm going to say Tom, all right? And I have the Boolean as true, right? Because I can turn it on. Right? Well, if I did this and I said, well, radio button's turned on, right? This Tom radio button. Well, what happens there when I do this, right? So true, okay. And if I was to run this thing, does it show me the button on? And even then, it doesn't show me the button being turned on. So it's some weird glitchy thing that is not showing me the button being turned on and off. It should be showing it to me right now. It shouldn't be turning it off because it's always true. So it's a radio button thing in IM GUI for STL. Don't know what it is. It's a glitch for sure. All right, so don't worry about it. I'm going to leave it as a radio button because I know it's there, right? You could certainly change it as a toggle, like a checkbox. So I want to check if one's checked, I can uncheck the other one. I could do that too. So when you check one, the other one unchecks. Then we know checkboxes work. And checkboxes have a value, right? So if one is checked, the other one is not checked. So you could have some logic that checks on and off radio buttons. It's up to you. And even if you were looking at the IM GUI, I've looked at the IM GUI earlier today, and if I was kind of this is the documentation. If I look for radio, it shows me the exact same thing that I've been using. Right? So this is the exact same structure that I've used in the past, and it worked before. Now it doesn't work. But you can always use colored buttons. You can say, I want to make my button color red or whatever it's going to be. And I can have as many colored buttons as I want, and I can turn one on and the other one off by changing the color of the button to green or whatever. There's other little effects you can try out to do it, to make it more, to give the user feedback that something is working. Okay, so it's really up to you how you want to make this work. I don't care. I'm making it work with radio buttons because that's the exact same thing. And yeah, Tam, you're right. It's just something that's glitchy inside of IM GUI on my end, not your end. Okay? It just doesn't work. We have a bit of a bug. So that's okay. I like it. It works now. And let's put this up on GitHub. So again, I'm going to go to Git. I'm going to say that, I kind of didn't do the right thing. I've got one outgoing commit. Sure, I'll do it that way. All right, so this is cool. I've got my stuff working, and it calculates the Manhattan distance or Euclidean distance by running. All right, so this does. So again, if I was to turn the grid on and I move things around and I check Manhattan distance, if this is the one we want to use, by the way, I'm choosing Euclidean distance first. I could change this to Manhattan distance first. It doesn't really matter, right? In fact, notice that when I do Manhattan distance, you can see this diamond that happens, right? You can actually see it, that it moves around if you look at it, if you try it out, where values to the right become higher than values to the left. It looks similar to Euclidean, but it's not as apparent because of the decimals, right? Same thing, it's just not as apparent, it's just bigger, okay? So again, it totally works either way, and all we're doing is calculating from each tile to the target where we want to go. Okay. So again, to support this, what I'm going to say is to start off, instead of starting as Euclidean, let's start off as Manhattan, because I think Manhattan makes more sense for us. We're in a grid system, and there's no need for us to switch to Euclidean unless we want to change something. So by default, it's just going to show us Manhattan distance. And we want to change to Euclidean, that can make sense if you want to change something around. All right, so that's the default. The next part is, now that we've done that, I want to start supporting new functions. So we've kind of done up to here. Again, this lab is going to be a little bit quicker than before because I've run through it a lot faster with you guys than with the other group. And that's just how it happens a lot of times. I want to start prepping for pathfinding for next week. And this is the next piece. We're not going to do pathfinding today. I'm going to just set up everything. So the first thing, I want to start setting up the tile status for both the start and goal tiles when I move them around. So what I mean by that is, by default, right, if I go back to here, when I'm in the start function, I want to kind of set up, remember there's different statuses, right? I don't want to check every tile. So here I've got a status of S, which means start, and a status of G, which means goal, right? But what if I had, as an example, some kind of wall here, right? And this status was a status of I. So here's eyes, right? And I want to put eyes here. So I would be impassable. So I make a wall that looks like this, and this from here to here is an outer elbow because I'm coming from start to goal, right? So here's an eye, right? That's a weird eye. How would I traverse to go from here to there now? Let's try and figure this out. So again, I'm starting here. I wind to the right. I go here first. I wind to the right. I go here next. I wind to the right, and I have this tile right here, which is 21, right? This tile right here, which is impassable, and this tile right here, which is 19. Guess where I would go? Here. Okay, I wind to the right. I have this tile right here, which is 20. This tile right here, which is impassable. This tile right here, which is 18. Where do I go? Here, 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 right? I go down actually with my winding pattern, right? I don't go up, I go down just because the way I wind, right? Then I go here, 15, and then from there I go 14, 13, and I'll keep going this way all the way across, right? Until I go to here, and then I go down here. That is going to be the way I'm going to traverse. This is going to be the path because I'm winding to the right. I'm winding to the right. If I wound to the left, right, as an example, and to try and resolve ties, right, then I would start. So if I was here, so if I'm here, instead of going this way, I would go this way, down, instead of right, right? So let's try that way instead. So I'm going down, down, down. This is the other way I would have gone, 18, 17, right? So let's see, I would have gone down to here, and these ones would be 16. Check this out, 16. And this is 15, and this is 16. Take a look what I would do if I wound to the left, right? So I started off on the bottom this way, right, every single time. So I'll go 18, 17, 16, and I'll keep going down like this. So I'll go down to here, right, to 14, and then I would, when I'm here, right, let's just complete this. This is actually incorrect. This is 17 here. I'll be okay. 19, 17, 16, 15. And then I would go 14, 13. And then bear with me while I'm doing this, guys. There's a point that I'm trying to make here. So this would be 13 and this would be 15. So I'm winding to the left, right? This actually would be, would this be 13? Or would this be 14 here? So this is 14. This would be 13. What about this one? This would be 15, right? Because it's farther out. I'm 14. I'm going down one. I'm 15 here. I'm 13 here. So I'm winding to the left, but it doesn't matter because each of these is 15. I'm going this way, right? And I would march down this way and across this way all the way until I got to the goal. So that's the difference. Is it a different distance? No, because there's more than one path to get here, right? It really depends on the way I'm winding, okay? And what I mean by winding is the way I check. I wind this way. I check this one, then I check this one, then I check this one, then I check this one. And if I found this one shorter first, I'm going to take this one first. I'm going to take the shortest number or the smallest number to the right, right? That's just the way I'm winding, okay? And this is if I have all of these tiles impassable, okay? All right, let's not make these tiles impassable. And I'm showing you this because this is, kind of an understanding of how things work with Manhattan distance, right? So let's just put all these in place here, and let's put these in place there, and there, and there. So I have this little grid for you guys so that you can visualize. I found that it was very useful for students when they first started off. Okay, so this is cool. I want to make another elbow down here, but I want to make an outer elbow. So I'll make an eye, impassables, that go like this. Okay, so let's make somehow my goal is inside of a room that looks like this. All right, so this is where the room is. Okay, now what would happen? What would happen now? Well, if I wound to the right, then I would go this way. I go round all the way here. I would come to 8, and then I would come down to 7, 6, 5. As soon as I hit this one, now I have 6, 6, 6, 5, and I have this one, right? So this one would be also 5, right? And this would be 4, this would be 3, this would be 2, this would be 1. I want to put this in place for you so you see this. I'm here. I came to here. And I want to go here, but all these are the same. All these are the same, right? They're equal. So remember, I'm winding to the right, and I've been winding to the right this whole time. So guess where I'm going to go? Here, right? Because this is sorry, I'm winding to the right. I'm going to start here. So I come to here, but I want to go back up. But guess what? I've already been there. And this is where we mark our tiles. We say we've already gone and done all this. These are all marked. These are all closed tiles, right? It's almost like I'm doing this. I'm saying closed, 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 right? I'm marching around this way, right? And then I come to here and I start going down, right? So I start going down here and I want to go here, closed, closed. And then I'm like here, uh-oh, where do I go? Well, I can't go up because I've already been there in this trial, right? I can go either left or right, but I'm winding to the right, so I'm going to go right. And this works out because I go here, and then I'm winding to the right. I can go 7 or 5, but 5 is lower. Here, here, here. Now, let's go back up, actually. So I'm here, and this would be 4, or because this is, look, this is 3, this is 4, this is 5, right? And this is 4, this is 3, this is 2. Okay, so let's think about this now. I'm here. I've passed this part, and I've got 5 here, 3 here, and 3 here. I'm winding to the right, which means I'm going to go here next, and then here, right? And then here, and then finally here. So this is the new path that I would take based on the fact that there's a wall right here. Okay, that's how it would work for pathfinding. Okay? So that's okay. But what if I reverse these? I'm winding to the right, and I want to reverse them. And again, this is an exercise that you need to do, guys, because you're going to get some weird solution, and you're going to go, wait, what? How did that happen? Because the way we're going to choose how to wind next week. Okay, when I say winding, you know, from here to here to here to here, I'm going to go in a clockwise direction when it comes to values. That's what I'm saying when I say wind, right? So let's switch this out. Let's do the other thing. So I'm going to say the goal is here and the start is here. And let's wipe out all these values instead. We'll leave the wall in the same spot, right? The wall is the eyes for impassable. But we'll kill all these things, okay? And we'll recalculate. So this is what's going to happen for you guys, right? So recalculating all this, right? And now we're going to start calculating, okay? So from the goal tile over, right, we're going to start going, okay, well, this is 1, this is 2, this is 3, this is 4, 5, this is 6, this is 7, this is 8, this is 9, and so on. Let's go this way and calculate the total distance. You can see that's 22 again. Over here, that's the goal. And this would be 4, this would be 5, this would be 6, this would be 7, this would be 8, this would be 9. Okay, cool. And this would be, you'd think that this is going to happen, but what's really happening is I have a 1 here. I have a, let's think about what's happening here. I have a value here. What value is this? So 3, 2, right? Right, because it's going over here. And what about here? This one. I'm farther out than 1, right? This is 0, this is 1, right? So 1, 2, 3. So here, this is farther out, so this would be, so how would this look? How would this work for you guys? What number would this be? This would be 2, this would be 3, this would be 4, right? That's what the distance would be from this to the goal, right? So the start to the goal is here, right? And it would be 21, and actually what it's going to be is the other way around. It's going to start off as, instead of these numbers, right? I'm just counting from here, but we should really count from here. 1, 2, 3, and so on, right? Because you start backwards, and this is what actually happens with your algorithm too, right? So here's 15, and this is 14, and you know, this is how it's going to work. It's going to go down here. Actually, this is 16. What am I saying? 16, 17, 18. like this, right? So this is, I'm just going to show you this. So this is all the way here to 22, 23 from the start. And then this would be the same thing. This would be 14, 15, 16, 17. Because we're going to move, but we're going to march back, right? 18, 19, right? 20, 21, right? And this would be 20, this would be 22, and this is going to be 23 because it's farther out. This would be 24 as an example. This is going to be 24, and this is going to be 23. This is going to be 22, right? Or 21 because it's closer. Now we're winding to the right. So wind, 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 wind. So we're going to go this way. So this is our first step. So we're going to go here, closed. We're going to go here. We're going to go here. Okay, cool. These are all closed. Now we're winding to the right. This one is actually closer than this one. Okay. I'm just putting it out there to you guys so you can see it, right? And this is where we can get into a little bit of issues, right? Because this is 21. This is 20, right? This is 19. This is 18, isn't it? And in fact, if we were to go there and we said this is 21, this is 20, and this is 19, we have gone there earlier. Let's take a look at these ones. So no, we would have gone here. No, we would have gone here because this is first. No, we would have gone here. Okay, now where do we go? We're here. So we go this way, or this way. Well, guess what? We have two choices, this way or this way. Which way would we go? This way. Is that the right way to go? No, it's not the right way to go. We should really go this way, right? Because this is actually going to cost us more time. But this is a path. This is the thing that pathfinding will do. Because this inner elbow, it's a use case that causes problems for pathfinding. That's why I'm mentioning it to you, right? Because it's going to be something that you're going to see that is going to pop up, and you're going to go, wait, why did my thing, why did it go that way? As an example, right? Why did that happen? Well, it happened because it's the way we're winding, right? We have an inner elbow right here, so like an inner wall. And we're going to wind this way. We're going to go here and here. Okay, now we're here at this point. We're in the corner, right? We've gone here. We've turned left because this appears to be closer to this through Manhattan distance. We didn't go this way. This was a pivot point. An inflection point is what we called it today in class, right? Where we decided to go this way instead of this way, okay? And there's all these are inflection points too. So here I am, and now I'm going to turn again. I'm going to change my direction. Okay, I didn't change direction here. I kept on going in the same direction. But here I changed direction. So this is an inflection point. Okay. Here I come to this point. I need to change direction again, right? I only have one choice. I can't go here. I can't go here. And I can't go here. I can only go here. So here. Okay. And I'm here. Now, where am I going to go? I can go here, 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 or here. Remember? Well, guess what? These two are the same. I'm winding to the right. I'm going to go back this way. Right? Look. Right? Because, why is that? Because I'm winding to the right. Right? I'm not going to go down here because this is the same value as this is. Right? So I'm going this way. Okay? This is the worst case scenario as an example, right? And then I can go two ways. I'm going to go this way. Uh-oh, I've hit a wall. Now I can go here, and that's the only place I can go, right? So I'm here now, and I've run all through this stuff. I can go here or here, and guess where I'm going to go? Here. So I'm going to go this way. I'm going to go this way, right? And I'm going to come down to this, and this one is going to be 20, and and this one's going to be 19, and this one's going to be 21, and this one's going to be 22, right? So guess where I go? I wind to the right, so I go here. I wind to the right. I'm only checking these two values. So I go here. I wind to the right. I can't go here. The only place I can go is here, right? But I've checked out this entire area, and now I start going back this way, finally. Ooh, man, what craziness, right? What craziness for me to get to that, all right? And that's why this route, that's why this is a point of inflection. And so is this, because I'm going to go this way. So these points here are a point of inflection, right? I'm going down here, point of inflection, point of inflection, point of inflection. Look at all these points here. And so what happens is these places present new opportunities for me to go the other way based on the way we're winding right now, okay? And then obviously when we come to this point right here, right, then this is a point of inflection, then we're going to go back the other way. And we're going to come to this point. And now from this point, 23, 22, 21, 19, 18, 17, this is 16, 15, 14. We're going to go this way. Why? Because we go up first, right? 12, 11, 10, and I probably miscalculated something because this should be like up here 10. Okay, like that. 3, 22, 21, 20, 19, 18. Yep. And then so it'll go this way. So it'll go this way up here. And then what's going to happen is this is going to wind up here. And then from here, it's going to go this way, this way, this way, all the way to the left. Because now this is the shortest path. This is going to be the shortest place to go all the way to this. And that's a weird way. You wouldn't have thought that this is going to be a thing. This is a point of inflection. This is a point of inflection. Okay. I would have liked to go this way. So what is the total distance? If I calculate the total path length now, path length is different than the distance, the total path. So what I'm actually doing is I went like this. Look, I went from here, I went up here, I went across here. So 1, 2, 3, 4, 5, sorry. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 5, 6, 7, 8, 9, 30, 1, 2, 3, 4, 5, 6, 7, 8, 38. That is the total path length that I took. Whereas if I went this way, I would have gone 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 2, 3, 4. 24. Is that the shortest way? Don't know. But it seems to be. Because I would have gone the other way around as opposed to like this really weird way this way. I mean, it could also be that this way is the shortest way. So something like, and again, you would explore all these paths, right? So 1, 2, like this. You probably go like down this way, right? And maybe that's the shortest way. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 1, 2, 3, 4. Same distance. So most likely you're going to find this distance first, right? Because this is the point of inflection. The first point of inflection, that's the point where you're going to try this other way out, where you're going to say, okay, we tried all this stuff. We marked all this as closed. Fine. Let's go back to this point here where we're going to try it from this way. Okay, so Tab says need cost as you go. Yes, you could. Adding cost from the current to neighbor and cost to goal. Yes, you could do that. You can also do other things too. You can also say, okay, what else can help us out? Because we're not using diagonals. If I was going to use diagonals, right? Let's undo those costs for a second, right? So 15, 16, 17, 18, 19. Let's do this again one more time, right? 21, 22. And I know this is tedious, but we need to, I feel that you need to understand, how this all plays out before it happens. Right? Before you get to the point where you're frustrated and you're like, wait, what? How is this even possible? Why is this working this way? I made a mistake with my algorithm, right? It's not like you made a mistake with the algorithm. That's how the algorithm would work based on our configuration, the way we're winding, the way we're the thinking that we're kind of doing and so on. Okay, let's get rid of all these points of inflections. So we'll just get rid of all the borders, no borders, okay? And the only thing we have is this wall again, this wall that's right here. Okay, this is our start and this is our goal. Okay, now what if we have these things, right? And we're winding to the right, normally. We're winding to the right normally. But what if both this one and this one, right? This one and this one, they both point to the left. So I'm going to try and go up first. And I run into a point where I'm blocked. This is where we had a problem, where we turned to the left because of this, right? And we didn't turn to the right because we don't know that there's a block over here, right? So this is where we can combine some things. And this is where people use kind of like the line of sight thing that we talked about in class today. So in our class, what we talked about is this, idea of points of visibility, right? Points of visibility. So in my point of visibility or line of sight, right, what I'm actually seeing here is where I'm drawing the line. So I draw a line, and I know that if I go up, as an example, I'm good to go up, but when I go up, I'm going to hit a line, and when I turn to the left, when I start looking left, I see a wall, right? In fact, I can start right from here, and I can start thinking about optimizations, right? I'm optimizing because I'm thinking about, I'm going to get into trouble using just Manhattan distance. So I kind of do something like this. I kind of cast a line, and I hit a wall, okay? So I know going this way is no good. I know going this way, that's no good, right? This way, I'm going to go to a dead end, like to a null pointer. And this way, I'm going to go to a null pointer, all right? But there's a wall here and there's a wall here, okay? These two walls. So guess what I'm going to do? What I'm going to do is I'm going to say, I'm not going to go this way and I'm not going to go this way because both ways, here and here, potentially there's a wall in both directions. I don't know if there is, but I'm saying this is just a point of contention. So which way do I go? I wind to the right and I go here. This is a new location that I've never gone before. Here, right? And this is based on line of sight. So you cast a sight line and then you detect to see if there's a wall in front of you, right? That's what you're going to do. So let me just color this with a different circle. Maybe make it a blue circle. All right, so we start here. This is our first position, right? Okay, cool. So we're at 23. We know that this is the start, so we're not going to start. But so we start there. We don't start here. We don't start here. Okay, now we start winding to the right. We start winding to the right, and we do the same test. We do our same test. We take our line, right, and before we start deciding which way we're going to choose next, we don't just wind to the right. That's our default heuristic. But we start casting a line. When we cast a line this way, we know there's a wall this way. But we're not going to check. We can't go back anyway because this is our start. But we know there's a wall this way. We cast this way. Oops, not this way. Cast this way with a line, right? Again, optimizations. There's no wall here. It's a null pointer. It goes right to the edge of the map. That's good. And you know what? We cast this way. There's no null pointer here. It goes right to the edge of the map. We know it's clear. So which way we go? We march to we use our right winding to go up. So we go to the next point up the chain, right, as an example, and we go towards the top. We go here, right? Okay, we do the same test here. We know we'd like to go this way, but right here, when we move to this position, we know there's something here, so we're not going to choose this one. We've already crossed this out. This is a C, right? So we go up here. And now we know that this one is no good, so we're not going to go there. We go up here. And, we know we're not going to go over here because of this thing over here, so we go up here. Definitely not going to choose this because it's an I, so we go here. And now we follow the rest of the stuff with our case where we completely avoided this little scenario. Guys, this is not a solution. This is a hack, all right? This is another type of heuristic to make us get away from doing stuff, but we're using points of visibility to help us out, to help us so that the AI doesn't get stuck. We've chosen a poorer path, a path that's taking longer, right? But we want to find the first viable path to get to where our goal is, right? And now we're going to ride the path all the way to here, right? And then we're going to go all the way left. That is going to be the path. And now look at that path. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 1, 2, 3. So that might be the shortest path. Okay, so that is something else we could think about doing as an optimization. I encourage you guys to look at optimizations because Manhattan distance and Euclidean distance are not going to be the only things, the only way that we're going to be able to conquer this using tile and grid system. If we had some other kind of system, if we're using like a graph system, if we can march diagonally, this might both cause us an issue as well as create opportunities for us, right? If we can march diagonally. Our assignment does not allow us to march diagonally. We can only march up, down, right, or left, okay? So again, using points of visibility might be one of the best ways to do that. Now, how do we incorporate points of visibility? Because line of sight is different than points of visibility. Line of sight is basically, I'm gonna collide with something that's in here. So the only way this would work is if we actually had an object that was in here. Like, for example, I don't know, we had a wall, right? I'm just gonna put a wall in there and we'll make it a different color, let's say a brown wall, right? So we had a brown wall that was here, like an actual texture, right, kind of thing, that was sitting there, right? And then we used line of sight and we detected there's a texture in front of us that we're colliding with, and it's in this direction. We also need to know which direction it's in. Well, it's in the up direction. So yeah, we can certainly do that, right? Or we can cast forward, right? We can move all the way up and then find that we're clear until we hit null pointer. If we hit an eye before we hit null pointer, right? We can check tiles, is what I'm saying, in all directions, right? Until we hit null pointer. If we hit null pointer, that's okay. That's a good direction to go because that's the edge of the map, right? If we hit an eye, that's bad. That means that that is not a viable direction. That is the direction we want to avoid. Don't wind to the right. As an example, go to the next possible square, but going in that direction, that's a bad direction. We're going to mark that as bad, right? But there's times where we can get stuck, right, using this system, as an example, especially when we have, a bad, kind of tile this way. Let's suppose we had even on this tile, there's some kind of eye tile, like it was like this, right? So we're using points of visibility. We can't go this way. We can't go this way. We can't go this way. So we decide to go this way, right? And now we keep doing that. And we can tell us with points of visibility, we say, well, we can't go in here. We can see that there's a block over here. So we're going to go down this way this time and up this way, right? And we're going to avoid going up here at all because of points of visibility. That's pretty cool, right? And that might solve a lot of our problems. It's just generating that point of visibility algorithm to optimize that's going to be challenging. All right, I'm bringing this up to you guys because it's going to come up in your assignment. You're going to get stuck. You're going to make some kind of wall or something like that. And one of the things I've asked you guys to do is make an interesting map. And notice that the switching this around, making this the start and this the goal, you should be able to do that in your assignment. I should be able to move my start and goal around to some degree. Now, in the assignment document, just to be fair, right? I think I allowed you to start with a fixed scenario. So I didn't say it has to be random or that you should be able to start with wherever you want to start with, right? Let's take a look at that assignment, okay, really quickly. Because we're going to move into the stuff that makes more sense, okay? So let's take a look here. So it says the place scene, you must use a grid of tiles, and each grid maps your cost value associated with passing through it. That was what Tam was saying. You can also make it so that there is like difficult terrain or whatever. It's up to you. That could also help. Grid of tiles with difficult terrain, that can help you select the cheapest tile as well, okay? And then, as an example, you have an actor sprite. You select an appropriate actor sprite, and please don't make it my spaceship. Make it your own. I've kind of mentioned this in the past as well. Make an interesting map. You can use a tile set or not. And then what happens is when you come down to the heuristic, it says when the user presses the H key, it kind of makes the debug view. The tile borders come on and all this kind of stuff. You can also use IMGUI if you'd like to instead. Now, here's the starting tile. Take a look at this. When and only when the debug view is active, the user can left click any open tile in the debug view and select it as the starting tile. That means that I can start wherever I want. That is the assignment. This will become a unique feature of the debug state, which means I can only select a tile in debug. That's the starting tile. And in the goal tile, I can right-click, any open tile in the debug view and select it as a goal tile. I would also allow you to use IamGUI, which is the way we're doing it right now, because that's just using the IamGUI to move the tiles around this way as well. I would allow this too. So move the tile around when you move it. Guess what? Now you have different start and goal tiles. That means I can literally do something like reverse the positions, and you should still be able to find, kind of a path, the shortest path, to this thing, which is exactly what I did with the example Excel file. You should still do this. You should still be able to do from here to there, So the scenario I'm mentioning, this one, which is the scenario with this situation, that is a viable scenario, So it may not be the same path, and especially because of this whole elbow business, This elbow business, this stuff when you're inside of a room or something like that, where you have some kind of block that goes here that's eyes, impassable. There's something you need to do, otherwise you're going to go like this, like exactly what I showed you. You're going to go back and forth and waste your time and eat up valuable path time instead of doing something that looks like this, across, or this down, Because remember, the path is only going to be as good as you program it. And that's why I said, think about optimizations later, like, some kind of point of view or line of sight or whatever you want to call it. Okay. All right, let's do some prep. This is part of what we talked about. First, I wanted to discuss this with you because it's going to come up, guys. It's coming up. When you do your assignment 2, it's just a matter of time when you run into this thing where you're like, wait, I'm stuck. I don't know why, but my AI is like hanging out here and just like it just keeps going back and forth, back and forth, back and forth. Yeah, yep, it's going to do that because it's the way you're marking tiles that are closed and open, You can also follow an algorithm that you find online from a pseudocode perspective, That might help you navigate some of this, but it's the situation I've put you in. Sure, you can find whatever algorithm you want, but we're in a box. I haven't allowed you to create an algorithm where you use nodes and connections. That would be a different situation altogether, Where maybe I don't have as many of these tiles and I have points of visibility where I can get to the map wherever I want. That might be something you want to deal with in the second half of semester when you do your pathfinding and steering behavior. Okay, so let's go into this. So what I want to do now to finish this off for today, so we did some of this, and we already have some screenshots where I can show Manhattan distance and Euclidean distance. And those are the screenshots you'd show for the day, okay? But what I want to do now is start thinking about setting up stuff from a placing perspective. So what I want to do is think about the structures that I need, So what are the data structures and stuff that I need? Well, I need a couple things here, I've got my compute tile costs, and I'm also going to have some other things in the future. There's going to be a function. Here's my to-dos, okay? Let's put the to-dos in place. Here's my to-dos. My to-do is going to be a function that's going to basically find the shortest path. So some kind of function that I'm going to call find shortest path. Okay, that's the function I want to make. The other one I want to make is some kind of function that displays, display the path list, whatever the path list is. There must be something like that. And there's going to be something that moves the ship along the path, So, something like move ship along path, something like that. Don't know what that's going to be like, but those are the functions I'm going to need. I need to find the shortest path, I need to display it in debug mode, at least, And then move the ship along that path. And it can't be automatically. It's almost like I want to chunk it. 1, 2, 3, almost like moving a piece in chess or on a game board, So there's you're going to see that, and it's also going to move in the direction it's looking. So that's something that I need to do. These are the to-dos that you're going to have for your assignment, okay? Next, I need some data structures, And these are potential data structures. Okay, potential data structures. One of them that you're going to need is maybe some kind of standard vector, right, of type tile pointer. That's going to be the open list. Something where I keep track of the open list. To be honest, I mean, you can have an open list and a closed list, and if you follow the algorithms, you can get to this. No problem. At the same time, I can have another data structure that looks almost identical, but is the closed list. So tiles in the closed list, as an example, that I don't want to go into. Okay, I've already gone there. And then finally, some kind of collection, which is the path list. Right, these are all the paths. I have a bunch of paths, viable paths that I've discovered. Right, and the path is, maybe each of the paths are going to have a length. Right. And, sure, I could have a path list as an example as well. It could also be that the path list is a vector of vec2s. A vector of vec2s, where the vector of vec2s is the path. That is the path. So I'm going to go from this grid point to this grid point to this grid point to this grid point. That is something that I can do here too. I mean, again, these are just some data structures that I'm thinking about for next week, right? As an example. And this is all prep. Okay, for this one. So I need some kind of potential data structures. I'm going to mark them as commented out because I may or may not use this stuff, right? I'm just pointing it out so that you can start thinking about how would you do it if you're programming. You're the developer and your boss has asked you to make a little pathfinding algorithm, right? I'm the boss, right? And how would you come up with it? How would you do it? Would you use path of visibility, right? So would I use path of visibility? I'm putting this in there for or line of sight. Would you use those two things to help you as an optimization? What would you do? If I can spell optimization properly, then maybe you can. Your boss doesn't know how to spell. Okay, how about that? That's a scenario. So think about this. This is what I'm going to leave you with today. I'm not going to go further than what I've done already. I've kind of created stuff. The one thing I want to do is set up our play scene by setting up our status. Okay, so when the target, right, and one thing that we're going to need for sure, remember we talked about the I, which is a status type, and G and S, those are status types. Let's do it for the scenes for my target and my starship, and then we'll stop for the day. Okay, just to get that part done, because I think I did that with the first class, and I think I'd like to do it with you guys so we can finish off and have everything that's the same. Okay, so here we're going to say that m_p target, right? The target is the goal, right? So we're going to say that wherever the target is, well, we already know where the target is. We can say m_get tile. So we use that function. The target is at 1511 starting off. We can set the tile status for that particular tile, the tile that the target is in right now. We can set the tile status to goal. That's the way we would set it. Once we set the tile status, remember, it changes what the status object is in there. And the same thing goes with the starship. We can set the tile status of the starship to start, and it's got to be in the same position, 1, 3. What this means is when we run the code for a second, right, then you're going to see that if I move my ship around, that my here, show what I'm talking about here. When I move my ship around now, and if I go do something like this, you can see there's an S there, right? S means start, okay? But when I move my ship, I want the S to move too, from here to here, potentially, right? So I need a way of erasing or resetting my tile status when I move my ship around. And when I move my ship around, also I want to reset the simulation because I don't want to calculate a new path. If I move my ship, I need to restart my path, okay? So that is going to be something I do in IMGUI. So when I'm moving, I want to do two things in IMGUI. First, I want to set the tile path in IMGUI to reset it. So I'm going to say m_get tile. I want to get the tile that the ship is in, as an example, m_p starship, and I want to get grid position. I want to get the grid position of where the ship is right now, and I can set the tile status to unvisited. So I'm going to say, when I move, set the tile status to unvisited. Okay, cool. And then wherever I land in the new position, do the same thing, but wherever I land, change that to start. Right? Oh, wow. There we go. Woo-hoo. All right. And it's the same thing for the target, right? So the target, let's set that to unvisited. Right? So now instead of the ship, it's the target. Missed. And let's set the target to goal before I recalculate. Right? So that is something we can do. And if I run this now, you can see that that moves my goal and start around. And you won't be able to tell because the start is actually underneath the ship. But what happens is it just rewrites the status, right, for the tile. Okay? That's important because if I move stuff around, I need to reset the simulation, right? The other thing is that I want to be able to, here's some to-dos for the IMGUI function. I'm going to put them at the top of the IMGUI function for next week. I want to put some to-dos, and one of the to-dos is going to be, I want to hide the starship and the target, right? I want to be able to kind of toggle visibility. That's what I really want to say. Toggle visibility only for the starship and the target. Why? Because maybe I want to do some debugging, right? And I want to be able to hide the objects and see the debugging view, or turn the objects on and hide the debug view. You know, I want to be able to do those kind of things. So that's something that we're going to work on next week. All right. All right, any questions around what we're doing this? So yeah, for the screenshots, I don't have a lot this week for you. The only thing I want you to do is for the screenshots, remember that there are, I definitely want to take a screenshot like this, where you see that this is Manhattan distance or Euclidean distance, and then switch it. Like actually move it around, right, in a couple places. Show that when you move the object around, it changes the distances, you know, from one place to the other, right? Doesn't matter. And really, we don't care about the ship at all. All we care about is the underlying tile. And this is going to be the same scenario that we have, you know, kind of going forward. Next week, if we have time, I'll also show you how to procedurally generate, you know, a map where I can select a tile already, right? And let's say, for example, I want to put a certain amount of mines, a minefield. I want to set a minefield up in this scenario, right? And how do I set up a mine so that the mine and the ship and the mine and the target, there's no overlap, right? Well, you can check the grid. If the grid already has a status, don't put something in there, right? Before you set up the, before you start the simulation. So you can click a button. It generates a minefield, which are kind of like obstacles, right? And this is where you can use your point of view or some kind of points of visibility, so you can decide whether you want to go left or right. And this is where it can get very complex, where your algorithm can spin and go up and down and around until it finds the shortest path. So be careful. The scenario that I mentioned here earlier was a very limited scenario, here. Because what if I have random obstacles everywhere, even an obstacle there, or there? I may have a point of visibility nowhere. For example, I have no point of visibility there, or there, and I'm in here. I'm in this point. Does that mean I shouldn't move? That's another scenario that you might get into. How far is the point of visibility? Is it within 1? Is it within 10? Is it within 3? That's another thing, another factor. Maybe that's another optimization, using points of visibility, but getting back a distance to where the next obstacle is, right? Something like that. And that's something that you can do to decide which way to turn. Okay, that's it for me today. Any questions around this? I know this is interesting for some of you. It's definitely interesting for me because this gives you, creates the idea or the illusion of intelligence for an object to move around the scene.
Yeah. So for 3 screenshots, you just want 3 different areas.
Yeah. Make it easy. Yeah, make it easy. I think that's the best way to do it. Yeah, I mean, I think there's really only 2 screenshots here. I can't really find 3 in this case, so 2 would be fine. I mean, I don't see it.
And
yeah,
it's a non-related question.
Sure.
I was looking at the course outline and it said we're doing lab quizzes with multiple choice and true and false. Have I been missing one, or is this the lab?
No, this is it. This is the lab.
Oh, okay.
Yeah.
Okay.
It shouldn't be. It should be lab. Lab should be all like practical labs.
It should be practical.
Yeah.
It just says it's tests, and yeah, it is the midterm going to be
true, false, multiple choice.
Okay, and how would we really prepare for that? Are we just using our own knowledge?
You're going to have it's open book, right? So it's not like you're going to. There's no shifty stuff around it. You'll have access to all these slides. And you basically, it's going to be from the slides. I'm not going to make new stuff up. It's going to be basically, it's not going to be, you're going to have a time limit, right? But and that's where the challenge is going to be. But really, it's just you having the material go through your head a couple of times, right? Maybe watching the videos, those kind of stuff if you need to. But you'll have a chance to do everything. You'll have the whole week to get it done, and you'll have 2 attempts. So.
Are any of them going to be like theory, or is it going to be like what is Manhattan distance?
It might be, yeah. It might be, yeah. It might be something silly like that, and it could be more complex stuff like what's this code do, kind of thing. Here's the code snippet. Which code snippet would you use for Manhattan distance? This one or this one? And then I mean it's fairly straightforward what you would use, but it's like if you've never done it before and we haven't talked about it, and if you weren't in lab, then it might be something that's challenging for you, right? But at the end of the day, none of this is supposed to trick you. I'm not going to try and trick you with the test. The test's goal is really for you to have this material go through your head a couple of times. That's what it is. And you should do fairly well on the test, and it should balance the people who had real challenges with the assignments, because the assignments are much more difficult, right? So it's kind of a balancing thing more than anything else.
Okay, so it's kind of like the catch up on marks.
I think so. I think it's fairly straightforward. But for some people, I'll tell you right now, no one ever gets perfect on it. I've never seen a perfect score on a test because of the time limit. You have a time limit. You have 2 attempts, but it's randomized multiple choice. So you're going to get random questions from a pool of, a number of questions. And then chances are you might get one you didn't see before, or you might get the same one and get it wrong. People do a lot of weird stuff. And they I haven't seen perfect marks on this one at all. So, okay. So it's not to trick you, but it's also supposed to challenge a little bit, right? So, people get really high marks on this one, but they, I think I've rarely seen a perfect one. How about that one? That's a better way of saying it. All right.
I'll challenge that.
All right. Cool. I want to see how you do it. All right. Anyone else have any other questions or comments before we go for the day? If not, then thank you so much, guys. Again, this is being recorded, so you always have a chance to go through and watch the video again. Otherwise, thank you so much for attending, and I'll see you all next week. Good luck on your assignment 2. Please don't forget to start, and don't forget if you're like someone who says, I can't see the assignment, it's because you haven't joined a group. Okay, I can't iterate or emphasize this enough. All right. Otherwise, that's it, guys. Thank you so much. I'm going to stop on YouTube, and that's it for today. Take care. Thank you.